everyone, welcome back to another chemistry lesson here about solubility and solutions. In the last lesson we talked about dissociation reactions, which are way at the beginning of my notes. Dissociation reactions are what happens when water dissolves something. So what happens is water molecules, when you put a solid in water, the water molecules kind of come over and they grab the molecule and separate it from the rest of the solid structure here, which is a little bit different with ionic compounds, because ionic compounds always contain positive and negatives as a part of that. So when an ionic compound dissolves, it always creates some positive ions and some negative ions. So you have, like, in a sense, two different chemicals that are created when one ionic compound dissolves. We talked about how they're sometimes present in different amounts. Like if there is twice as many chloride ions, you would have more of the chloride in the solution. By the way, I apologize about this watermark on the notebook file. I need to figure out a way to get rid of that. I have to probably upgrade to a premium version, which I don't have at home. But if you're following along in the notes that I put on Classroom, I thought it would make sense to do what are called the solubility rules and net ionic equations as the next lesson, because they kind of go along with the dissociation reactions we already wrote out. It turns out that most or a lot of ionic compounds do not dissolve in water. Actually, a couple of the examples on your worksheet are not really even soluble compounds. What that means is that when water molecules come to try to approach them, only about maybe one in every 1,000 ions actually separates. So a small amount of the ions do separate, but the vast majority of them stay stuck together. So the reason this happens is that the bonds between the positive and negative are stronger to each other than they are to any of the water molecules trying to separate them out. So there's actually a lot of different combinations of ionic compounds that don't dissolve in water. So we kind of learned that all ionic compounds dissolve, but there's actually a large number of them that won't dissolve in water. So what I want to do with today, what I want you to be able to figure out by the end of this video, is how you can predict whether something dissolves or not. So there's a couple different ways to teach this, but there's one way that I like to teach my students to remember what dissolves and what doesn't is with an acronym. The acronym is CASH and GIA. CASH and GIA is, that should be a capital N. CASH and GIA is an acronym for all of the ions that dissolve. So these stand for like chlorates, acetates, sulfates, those things. These are usually soluble ions. I write it as two different words because the negatives first and then the positives. It's easier to figure out by looking at the negatives, honestly. So these are the things that typically do dissolve. Let's go into a little bit more depth in this. So this is what the different letters stand for. So C is chlorates, not chlorides. So if you look on your periodic table for polyatomic ions, if you look on the back of it, there's actually quite a few that look really similar. There's chlorates, chlorites, hypochlorite, and perchlorates. But we're only talking about the one here that says ClO3, chlorates. Acetates and sulfates, you know what those are. Halides, which are those are your halogens that end in ide, so chloride, bromide, and iodide. They all sort of follow the same trend. And then the other negative one is nitrates. As far as positive things that always dissolve, that would be all of group 1. So that's the G1 here, is the group 1. So all of group 1 is on the front side of your periodic table, just that first column. Not hydrogen, just the lithium, sodium, potassium, rubidium, cesium, etc. And then something that always follows the same trend as group 1 is ammonium, NH4+. So all of these always follow the same trend. There's no exceptions to any of the positive ions. They're always soluble. So ammonium and lithium, all group 1, are always soluble with no exceptions. Chlorates, acetates, and nitrates also have no exceptions. So anytime you see a nitrate or an acetate or a chlorate, those things have to dissolve in water. There's no exceptions to those. There are a couple exceptions to sulfates and halides, and those I have listed as exceptions on the back of your periodic table. So I'm going to scoot this down so I can write some exceptions in here. So there's a couple sulfates that do not dissolve. So sulfates that don't dissolve would be anything that has a group 2 metal of calcium or below. So that would be calcium, right? So calcium 2 plus, barium, strontium, and also a couple of the heavy metal sulfates don't dissolve as well. Silver and lead are two good examples. So these are the only combinations with sulfates. So calcium sulfate, strontium sulfate, silver sulfate, those are the only sulfates that do not dissolve. All other sulfates dissolve. Okay, so I'll color code that, and you so you can kind of follow along there. And then for halides, almost all halides dissolve, but they have a couple similar exceptions as the sulfates. So halides, which again are Cl minus, Br minus, I minus. There's a couple that do not dissolve. I figured this would look a little bit nicer than me trying to draw on it. So the halides that don't dissolve are also some heavy metals. So again, silver and lead. But then we also have copper 1. So copper 1 is an ion that we don't use very much. Normally we're talking about copper 2, but just copper 1. And then mercury, which we don't hardly use at all. So silver and lead are really the only big exceptions that you should know for your halides. So all other bromides, iodides, all those dissolve except for those couple exceptions. I'm going to change it to purple so we can kind of, and then I'll shrink it down so that it's off to the side. Again, I'm sorry about this watermark. That's kind of disrupting how I was planning on doing this. Okay, so if you're confused by this acronym, there are solubility rules on the back of your periodic table. It looks like this. So you have this box right above your electronegativity chart that looks like this. So what this is basically just a little chart that describes exactly what I just said. So any of the things that are not part of Cashingia, so carbonates, thiosulfates, phosphates, cyanide, things like that that I didn't list, you just assume that those are not soluble. Okay, so anything that I didn't list at all, you should just assume is not soluble. So a lot of my students just figure this out right away, and then they either do them all right or they do them all completely backwards. So let's try to figure out a few of these I have as examples. Sorry, my smart notebook file crashed there for a second. So what we're trying to do is we're trying to figure out if an ionic compound, which is always a positive and a negative, if it will dissolve in water or not. So I have some examples here. Let's see if we can figure out if each one of these is soluble or not. So it usually takes a couple before we can figure it out. So ammonium in nitrate. So if I'm going from the acronym, here, ammonium is the A and nitrate is the N here, and so these things, I keep switching to lowercase, I don't know. So these things are always soluble. So not only is the positive always soluble, but the negative nitrate is always soluble. So for that one, I am going to put that this is definitely soluble. Okay, because not only is the nitrate always soluble, but the ammonium is always soluble. So that one is a definite yes. Phosphate. If you look on, phosphate's not part of the Cashingia. If I go back, phosphate's not part of the Cashingia. But sodium is a group 1 metal. Group 1 metals are always soluble. If you look at the back of your periodic table, the first thing that's listed here, Group 1 ions here, those are always soluble, no exceptions. So if I go back to my example here, sodium is a Group 1 metal, so this one has to be soluble also. So that's for sodium phosphate is also soluble. Calcium sulfate. So I remember sulfate is the S in cation. So sulfate is okay, so that should be soluble, right? Well, unfortunately calcium was one of those couple exceptions that we listed. So calcium sulfate is not soluble. So if you look on the back of your periodic table, the ones that are not soluble, the sulfates, calcium, strontium, barium, silver, and lead, those are not soluble. So calcium sulfate is not soluble. Mercury 2 bromide. So mercury is a heavy metal, and bromide is one of your halogens. Oh, Ivy wants to say hello. Come here, sit in my lap, honey. Say hi. Hi, everybody. They can't see you, I don't think.
Hi.
Hi. Maybe I can move the camera here. Say hi.
Hi.
Okay.
They're not saying hi.
Well, you're not gonna. I'm just recording, honey. I'm sure they'll appreciate you saying hi. I'm almost done here. Then we can take a walk, okay? Bromide is one of your halogens. So a halide, bromide is a halide, so it should be soluble. But if we look at the back of our periodic table, there's a few exceptions with that as well. So bromide is one of your halogens, but you see there's some heavy metals that don't work with that. Silver, lead, copper, and mercury. So mercury bromide is not soluble. Okay, we'll do a couple more of these and see if we can figure them out. Silver chlorate. All chlorates are soluble. No exceptions on chlorates. That's the C in Cashingia. So that one is soluble. And then if I look for silver chloride, chloride is a halide. And so there's a couple exceptions for halides. Remember, sulfates and halides have exceptions. So if I look for that one, chloride, silver, lead, copper 1, and mercury aren't soluble. So that silver chloride is not soluble. On your worksheet that I'm going to post tonight, I'll pull that up so you can kind of see what it looks like. This will be one that you can just edit. If I'm looking at this, so I need to sort of decipher my positives and negatives. So this is ammonium acetate. And ammonium and acetate, those are both always soluble ions, so I'm going to write that this is soluble. Barium hydroxide. Barium hydroxides are usually insoluble. There is a goofy exception listed on there that barium hydroxide is soluble, but that's really tricky and it hardly ever comes up. But I'm going to put that barium hydroxide is soluble, and that's probably not a good one to lead off with. Iron 2 carbonate, which would be FeCO3. Iron 2 carbonate. I gotta look on my chart. I don't see carbonates on there. Carbonates are usually insoluble, except with group 1A. And iron is not a group 1A element, so that one is not soluble.